Yeah, as Joe said, I'm going to talk about how stochastic fluctuations can do something interesting. And this is very much related to what Scott was talking about yesterday. But I will give you a little bit different kind of picture perspective. And yeah. So the system I'm concerned with is this type of experiment. Basically, you have antiferromagnetic insulator sandwiched by two platinum leads. And one is the detector, the other is the source. So, okay, what people are doing is, you push your current through the platinum. Okay, this current is constant. And then, you see somehow spin current is driven through this structure. And in that situation, if from the perspective of the antiferromagnet, nothing seems to depend on the time. So then how can you drive the spin current? And basically, spin current must be carried by the dynamics of the nickel oxide in this case. So then how can it, so anything, nothing is time dependent. How can you drive the dynamics of the antiferromagnet? That was the question. And this is very naive. Sorry, yeah, this question is very, very naive, of course. So, to explain the true meaning of this question, I think I need to spend much more time. But I'm not going to do that. And so I hope at the end of the talk, I guess this meaning of this question will be a little bit clearer. And yeah, so this is one of the, I think, hot topics currently in the spintronics, as well as in this workshop. Many people talked about the same sort of experiment theory. And I just mentioned one experiment from Moriyama-san. And this is conceptually exactly doing the same thing as I mentioned. So you inject the spin from the platinum and then detect it somehow by the damping change. But I don't talk about it anymore. It's there's an expert here. So of course, there are many theoretical attempts as well. And then in my opinion, there are three camps. One is these people, Resende, for example, start from Boltzmann equation for magnons, and then eventually derive the diffusive equation and use it as a spin transport. And these people did proposed the spin current carried by the evanescent mode. And then this Scott work, which is a linear response theory, essentially, to the spin accumulation at the interface. And this is also utilizing the stochastic methods, which I'm going to also use. But my perspective is a bit different. So I want to focus on two well-understood phenomena in spintronics. The first thing I talk about is spin-Seebeck effect. This is really the most, I think, obvious example where spin current is driven by the random fluctuations. And I'll just give a review from my perspective. And the second aspect I need to explain is the damping-like torque. And this is also very well understood. And this physics here I'm going to discuss will be very much the same as the magnetic switching. Then I argue that understanding these two phenomena, you can immediately understand the current, spin current transmission through antiferromagnetic insulators. So the take-home message for me is damping-like torque plus thermal fluctuation by themselves will be enough to generate a spin current. So I start with the spin-Seebeck effect. And so dynamics of the spin is fundamentally a precession. So if you look at a single spin in a magnetically ordered material, the picture looks like this. So you have an effective field, which is usually along the direction of the magnetic order. Then around this magnetic field, the spin precesses. This is the mode of the dynamics, and this is the only mode of the dynamics in most cases, I guess. And so it feels this torque perpendicular to this field and this spin. This is the first kind. This is the conservative force. So this can be written in terms of Hamiltonians. There's another kind of force, which is damping. So this tries to bring the motion of the spin back into this static configuration, which is along this effective field. So this is damping-like. So what it means is, you cannot write it as a Hamiltonian conservative force. So the nature of these two forces are completely different. But there are only these two forces, essentially. And the mode of the dynamics is always a precession. And the precession is inherently chiral and non-reciprocal. What it means is, okay, in this picture, okay, it can rotate only in this counterclockwise direction, not the other way, never. So it's chiral, it's non-reciprocal. And this results in the angular momentum. So this precession always carries some dynamical angular momentum, which is given like this formula. So it's m cross dm dt. And so precession is always a kind of dynamical angular momentum. And this is the nature of the spin for the spin waves from classical perspective. By the way, I'm going to mostly stick to the classical picture in this talk. So now, okay, it was a deterministic dynamics. But even in a random situation where there's thermal fluctuation, this is due to, I owe this perspective to Saito sensei, but he explained it in this way. So okay, you have the thermal fluctuations. So this randomly knocks off these spins. So the trajectory must be very complicated in general. But even so, between the two knocks, say, okay, this motion must be precession because that's the only mode of the dynamics. Then this random motion still has some chirality and some non-reciprocality. So on average, these fluctuating spin can rotate only counterclockwise again. So not the other way. Then this handedness again generates some angular momentum. So it's very strange because the motion is completely random, no directionality in it. But automatically spin converts the completely white noise into a particular an angular momentum with a particular orientation. So in some sense, spin is a ratchet. So it converts the random motion into rectified that random motion into one orientation.
Why is counterclockwise only?
Well, it's not necessary. I mean, it depends on your, I don't know, things like magnetic moment, charge, things. But
why it's only one direction?
That's again because your effective field is pointing in one direction. With respect to this field direction, you have only one direction. That's the point. I mean, I'm always assuming there is an effective field.
Okay. So the effective field would be that.
Yeah,
the mean field of the.
Yes, that's the yes in the ordered material. That's the mean field coming from the order. Yeah. Okay. Yes. Exactly. So this gives you the even in the thermal fluctuation, you have non-zero expectation value of this dynamically generated angular momentum, and this is the essential source of the spin-Zebeki effect. So I mean a bit more of mathematics. So random precession, okay, as I said, okay, non-zero angular momentum expectation value. So angular momentum is roughly given by this, and then this delta m, okay, fluctuating part of the magnetic dynamics, okay, has non-zero expectation value like this. Okay, if you raise the temperature, okay, that means okay you have more fluctuations, and this is a kind of fluctuation-dissipation theorem. I'm going to talk about it a little bit later. But usually, okay, you take this fluctuation amplitude to be proportional to T. This is a high temperature approximation, by the way. It's not correct for the entire energy. But for the time, I mean, today I'm going to talk about only qualitative features, so this is enough. And then if you increase the fluctuation, this fluctuating angular momentum should also increase. So this means temperature can generate the angular momentum. So what happens is, okay, the original length of the spin will be like this, but it starts to fluctuate by the temperature. Then if you take the average, of course, this component will be reduced. And this reduction of the magnetization corresponds to the generated angular momentum. And this represents the heat spin conversion. Of course, this is very familiar. I mean, in the magnetic, say, ferromagnets, it's very well known that the magnetization scales like this. And so if you raise the temperature, I mean, this part generated will increase. Of course, actually, by the way, this cannot be derived from this expression, so that's why I put this approximation thing. So it belongs to a different approximation. But qualitatively, I mean, the same physics. So the question is, of course, this generated angular momentum, is it useful for anything? The answer is no, if the system is in equilibrium. So as an example, I think I talk about this simple structure, junction between ferromagnet and normal metal. If the temperature of these two are the same, okay, you have the fluctuation here, angular momentum generated. So this tries to flow out from this magnet. But on the other hand, on the normal metal, okay, you have electrons flying around. So these guys hit this interface randomly, and then this generates some force onto this magnetic moment. And of course, it's very hard to say anything about the details of this force. But by assuming this is in equilibrium, I mean, it's good to cancel this flow of the spin. Otherwise, there will be some transport current. Then this is against the assumption of equilibrium. So if the temperature is the same, there must be a complete compensation of the spin current going from and into the ferromagnet. But once you drive the system out of equilibrium, say you lower the temperature of this normal metal, then there's less fluctuation in the electrons. So the force exerted by the electrons will be smaller than this situation. But this automatically means, okay, there is going to be some flow. Because, okay, I didn't change the fluctuation here. So this gives you a net spin current. And this is the simplest explanation of the spin-Seebeck effect initially put out by these people. So this is more or less what I wanted to say about spin-Seebeck effect. Any question? Okay, so I move on to the next one. So this is a spin transfer torque. Very brief review of spin transfer torque. So this is called also Slonczewski-like torque. So what the assumption is, okay, you have the interface. Electrons are hitting the magnet. And you have the direction of the magnetization. Okay, you take the quantization axis to be this direction. Then the scattering of the electron does not flip the spin. That's actually very counterintuitive, because if it doesn't flip the spin, it cannot excite spin waves. But this is quantum mechanics. So electrons have a phase. And then upon the scattering, the phase can change. And it turns out that when the phase acquired by the scattering differs between the upspin and downspin, then there will be some net spin current flowing across the interface. This is the spin transfer torque. I mean, damping-like spin transfer torque. And this is the idea of Slonczewski. It's very quantum mechanical because it depends on the phase. It's not a spin flip. It's just a phase difference. And so this is very remarkable, but I mean, this seems to be what we are observing. And the effect of this spin transfer torque is well known. I mean, it's going to add a term in the dynamical equation of the magnetic moment like this. So this is damping-like torque. So I'm going to use this term throughout. So if you include this torque, your Landau-Lifshitz-Gilbert equation just looks like this. So the effective field I talked about, this damping, I also talked about it. And it just looks like this. But for the sake of the discussion, so eventually I'm solving these equations to get physical quantities. But for the sake of the discussion here, I think it's better to write it in this way. So this is called Landau-Lifshitz equation. What I did was simply substituted this m cross h into this dm dt. So it gives terms like this. So it's ignoring the higher order terms in alpha and this spin current. But for the timing, it's OK. And then from this expression, it's clear that what this spin torque does. So let's say if the spin torque is parallel to the effective field, okay, it simply shifts the damping constant. So damping constant is shifted by this quantity. And of course, this is well known and mentioned everywhere. But the important thing is, okay, the signature here of the spin current can either increase or decrease the damping. So damping can be modulated by the damping-like torque. And of course, this is from the beginning why it's called damping-like. I think I used too many equations, so I just give you some pictures. Okay, so when spin current is polarized along the effective field, this enters, then this enhances the damping constant of this precession. So it's intuitively clear, because if you inject the spin along this direction, okay, eventually you prefer to align that spin into this direction as well. So that basically enhancing this restoring force. On the other hand, if it's opposite direction, okay, that damping is reduced. So the spin wants to go away from this side. So this is, of course, the fundamental mechanism of the switching. So there's going to be a threshold current. If the threshold, this spin current exceeds the threshold current in this direction only, then this is going to switch. So these dynamics, okay, so far I talked about the torque only, but the damping-like torque itself cannot do anything. It cannot induce the dynamics. It's just damping. What I mean by this is, if you try to solve this LLG equation with the damping-like torque term, if the torque term is constant, eventually this M will just settle down to this equilibrium configuration. Basically, M is just aligned with effective field. I mean, this is just very obvious, but then it seems like, okay, damping-like torque cannot do any dynamics. But that's not true, because there should be always some random fluctuations. So what I mean by random is, okay, its average is 0, but its second moment will be non-zero. So you add this random force field into your equation, this term. Then this term, crucially, depends on time. So this drives the dynamics. So this is the source of the dynamics. So that's why I'm saying, okay, it's driven by stochastic fluctuations. And so this one is the cause of the dynamics. But I'll show you this damping-like torque does something interesting too. Now I'm talking about the stochastic differential equation instead of just a usual differential equation. So to solve stochastic differential equation means something a bit different from usual. So it means, okay, you know the so when you say you solve the equation, when you know the probability distribution of your variable P of M, so you want to know this quantity. And then, okay, to know this is equivalent to know all the expectation, all the higher moments of this expectation value. This is what I call the solution of the stochastic LLG. And then if there is no spin torque term, the solution is kind of obvious. It's going to be the equilibrium solution. So equilibrium solution means, in terms of the distribution function, it should be classically Boltzmann distribution. Okay, of course, if you go to quantum mechanics, it's got to be, in this case, Bose-Einstein. But anyway, some equilibrium distribution there. So this should be satisfied. But for this to be satisfied in the absence of the torque, there must be a specific relation. So this fluctuation amplitude of this random field must satisfy this condition. This must be satisfied to get this solution. So this is fixed by the requirement of equilibrium. And this is called fluctuation-dissipation theorem. So this relation is really important. So this basically says, okay, this fluctuating field is proportional to the temperature and also the damping. But if you add the spin transfer torque, this FDT is going to be broken. So spin torque modifies the effective damping, as I said, so depending on the signature of the spin. And I have to make the assumption that this random field does not change its amplitude. This is an assumption, I mean, no proof, but it's typically taken in the context of the magnetic switching. And I do have some microscopic results which kind of support this. I mean, it's modified differently in the presence of the spin current, but let's say let's take this assumption for the time being. So then what happens is, here the damping is from the intrinsic one in the absence of the spin current. But now the effective damping is modified by the spin current. So the balance between this damping and the fluctuation is now broken. And the fluctuation-dissipation theorem doesn't hold anymore. But this is kind of the same thing to say that the system is out of equilibrium. And we have to be careful about the temperature. So I'm calling temperature, but now the system is out of equilibrium. So you cannot usually define the temperature. But here I'm assuming that there is a heat path, usually phonons, and it sets the temperature. So this is T. So whenever you go out of equilibrium, we just have to be very careful about temperature. But yeah. Again, I think there was too many mathematics. So again, some pictures. So you inject a spin, and then if it's parallel, the damping is enhanced, but the fluctuation stays. So the random field stays the same. That means the amplitude of the fluctuation of the spin will be reduced. But that means, the dynamical spin is also reduced. This is the situation when they are parallel. When they are anti-parallel, it's the opposite. So damping is going to be reduced, but the random field will be the same. That means, the fluctuation will be bigger. So more fluctuation, more spin. I just said that temperature cannot be defined in non-equilibrium circumstances. But in some cases, you can have a reasonable definition. In this simple setup, sometimes you can solve this stochastic equation to get an analytical solution. Then it happens to look like the Boltzmann distribution. But the temperature is not the one given by the heat path, but it's modified by the spin current. So you can talk about this effective temperature generated by the spin current. This is not a thermodynamic temperature, but it's a nice picture to have. So in this setup, what it means is effective temperature is reduced. So what happened? Effective temperature is reduced means this arrow represents the dynamically generated angular momentum, which is pointing the other direction. So this was in equilibrium, but because the temperature was reduced, it's going to be reduced. And then the other way happens like this. Simply the effective temperature is the opposite. So this dynamically generated angular momentum will be increased. And this difference will be essentially the difference in the temperature. So this is just a picture applicable only to very limited situations, but it's useful. Very qualitative.
Can I ask a question? So you said in equilibrium you get with this white noise correlator Boltzmann distribution, but shouldn't you get a Rayleigh Jeans?
Yeah, good point. So actually, I'm a bit confused about this as well. So Langevin equation, linearized, you solve it, then you get Rayleigh Jeans. But Langevin equation is usually equivalent to the Fokker-Planck equation. Then you go to Fokker-Planck equation, you solve Fokker-Planck equation, you get a Boltzmann distribution. So they are, I think, corresponding to each other in some ways. But actually, I'm a bit confused as well. Yeah.
Isn't that because of the high temperature limit that you take?
So the Rayleigh Jeans distribution is also in the high temperature approximation. High temperature, this proportionality approximation. Yeah.
Like I wonder if it's that you turn off. It's like kind of the zero energy limit that you get this large distribution of Rayleigh Jeans, which means that you have these huge fluctuations because you have no gas. But then that's exactly where linearization would fail.
Yeah.
So maybe that's the way.
Yeah. Any other question? So then I talk about the antiferromagnet. Again, I take a very simple model. So antiferromagnet is just say coupled ferromagnets. But this coupling is of course exchange, and it's going to be very strong. But for the timing, I ignore this and then think about the intuitive picture. So you inject the spin current like this. Then for this sublattice, it's parallel, so the damping is going to be increased. For this sublattice, okay, it's going to be decreased. So okay, yesterday I think Scott was emphasizing that to drive the spin current in the antiferromagnet, it's necessary to break the symmetry between two sublattices. And the damping electrode does it by distinguishing the damping of these two. So the equations of motion for each spin are really essentially the same as before. The effective field is again along the direction of the order parameter, so it's opposite for the opposite sublattice. And then damping is modulated by this amount proportional to the spin current as well. But the important thing is, of course, this effective coupling does include the effect of the strong exchange interaction. This has to be taken into account. But otherwise, I mean, there's nothing really different from what I've been discussing. So very qualitative picture. So spin transfer torque gives you the opposite damping modulation to the two sublattices. But then qualitatively, you can think of that as generating different effective temperature for different sublattices. So what happens is the fluctuation in one sublattice is going to be suppressed, but the other is going to be enhanced. So this generates this dynamical angular momentum. Okay, in this case, okay, in this sublattice, it's going to be smaller than the equilibrium angular momentum. In this sublattice, it's going to be larger. And in the equilibrium antiferromagnet, these two generated angular momentum exactly cancel, so there's no net magnetization. But in these circumstances, clearly there is net excess. So this induces the total net magnetization in the antiferromagnet. And this net magnetization is also non-equilibrium quantity. Again, I made some assumptions about the random fields, but actually these assumptions are almost completely specified by the equilibrium fluctuation-dissipation theorem. So far I've been talking about only the magnet, but the structure I want to talk about is, okay, antiferromagnet attached with another normal metal. What happens in this case, if you have the dynamical angular momentum in it, then there's a spin pumping. So this dynamics induces the spin current to the other material. And then, as I said, in the equilibrium condition, these two must be always cancelled. But in this situation, if you inject the spin current, this system is already out of equilibrium. So there must be some current flowing in it. Even without any temperature difference between the two. Temperature, I mean thermodynamic temperature. Effective temperature is different. So this does induce some current. Then, okay, this angular momentum here is just a sum of these two. It's given by this formula. But this L, so L is the L vector. But this L cross dl dt is exactly what appears in spin pumping formula. So spin pumping is usually given by this spin current going out. Is given by the kind of normalized spin mixing conductance times this dynamical part of the angular momentum. But as I said, okay, this generated angular momentum is essentially given by the difference between the two temperatures. And this is, of course, proportional to the spin current injected. So this is the essential mechanism of the spin transport as far as I understand. So simply, any out of equilibrium magnetization generated in the antiferromagnet will try to flow out and then induces some spin current. And this spin current does not stop until the system settles down to equilibrium. But as long as you keep driving the system, okay, it stays in out of equilibrium and the spin current keeps flowing. So this is the answer. But all these were possible only if you consider that this fluctuating random field that is driving the dynamics. So damping torque itself cannot do anything, but the combination of the damping torque and the thermal fluctuation generates the spin current. So this is essentially what I wanted to say. So this is the final slide. So far, everything was really qualitative. But I don't want to show you the equations. But OK, what I haven't discussed is the effect of the strong exchange interaction between the two sublattices. So to quantify that, OK, you just have to solve the real dynamical equation for the antiferromagnet. So I did it for, say, nickel oxide model. So it's 1-1-1 plane. So you have easy plane, easy axis, hard axis anisotropy, and then 3 easy axes in these directions. So I just take this model and solve the LLG. And then I plot the result. So this is the induced magnetization in the unit of the thermal fluctuation already existing in the equilibrium. So the dependence here is on the ratio between this easy plane anisotropy and easy axis anisotropy. What this shows, OK, if it's 0, here it means, OK, the system is uniaxial, so only easy axis. And then you see that the spin transmission is maximized at the uniaxial case. So uniaxial is always preferred in this context for the spin transport. Then once you start increasing this biaxial part of the anisotropy, it decays like this, depending on how strong the spin current is. So delta alpha is basically the spin current. And so this is intuitively, actually quite intuitively, if you go to a magnum picture, it's sort of clear. Because in the uniaxial situation, you can define the magnum spin. So magnons can be chosen to have spin plus minus 1. But once you go to biaxial or any other type of anisotropy, usually the spin wave modes, eigenmodes, are linearly polarized, and they don't carry spin. So that's showing here. So it's usually, so the message I want to convey here is usually uniaxial is preferred. But on the other hand, even if it's not uniaxial, OK, it's not going to be completely 0. It just decays like this. So essentially, this is just solving the equations. So in principle, I can say derive temperature dependence, thickness dependence, but it's a matter of how complicated the model can be and how much you can do in practice. OK, so this is more or less everything. So summary. So the first message is spin is a ratchet. So it generates the random motion. So it generates an angular momentum from random motions. And then in the equilibrium, this angular momentum generated by random motions cannot do anything because of the fluctuation-dissipation theorem. But if you apply the damping-like torque, it's modified, and the system goes out of equilibrium, and the spin can flow. And then in the antiferromagnetic case, damping-like torque distinguishes the two sublattices, breaking the symmetry, and it generates the out-of-equilibrium magnetization. And then this is converted into the spin current by the spin pumping. And yeah, so this, I really have to acknowledge Helen here. I mean, this whole story really came out spontaneously out of our discussions. And also Darcy, who really keeps me being interested in this type of systems. And I also really thank Hiro and the money with which I can do this research. Thank you very much.